morning or good afternoon, depending on where you are. We are continuing with our thermodynamic lectures. Today we want to look at gas power cycles. And we want to look specifically at the Brayton's cycle, or what is also normally referred to as Joule's cycle. Now, in Brayton's cycle, we are going to use air as the fluid. That is, gas is the fluid. Gas is the fluid. In Rankine cycle, we had used steam. In Carnot cycle, we had used an ideal gas. So in this particular case, so you expect Brayton cycle to be a little bit closer to the Carnot cycle than it is to the Rankine cycle, or to the interfaced Carnot-Rankine cycle. So here the fluid is gas. And it has 4 steps, basically. We have, in the cycle, we have 4 steps. 1, we have adiabatic compression. You can still consider this also as an isentropic process, because remember, we said that from Clausius inequality, ds equals dq over dt, and so when that is 0, it's isentropic, therefore equals to 0, then dq will be 0. So that's a adiabatic process. So that is adiabatic compression. It also has, in the second case, we have expansion but under constant pressure conditions. We have isobaric process, type 2. Then we have the expansion process, when those vapors are in the turbine, expand, doing work. That's the piston cylinder work, reciprocating work. So we have again adiabatic expansion. And during this particular process, heat is added in step 2, where we have a isobaric process. Heat is also added into that system. And then we have the 4th one, which in itself is again isobaric process. Heat is extracted. Let's just use the word rejected, it's more appropriate. Now, we can illustrate these 4 steps. We can illustrate these particular 4 steps in PV diagram and TS diagram. So if you look at the PV diagram, we have pressure, we have volume. Pressure, we have volume. And so this particular process we have state point 1, state point 2, state point 3, state point 4. This is compression. This is isobaric. You can see it's constant pressure. Let's call that P2. Let's call that P1. This is an expansion process. And this is also isobaric. Here we have heat being put in. Here we have heat out. That particular process. Now on the temperature entropy diagram, let's put them side by side. Entropy, temperature entropy diagram. That's the TS diagram. temperature. Let's have it here. And let us have entropy. Draw the axis properly. And so we have state point 1, state point 2, state point 3, state point 4. These are isentropic. And we have just explained on the Closures inequality that they are basically adiabatic. This is also isentropic. It's compression, but it's isentropic. This is compression, but it's isentropic. It's expansion, that is isentropic. And these steps 2 to 3, 2 to 1 to 4 are all isobaric. Isobaric, isobaric. So we just have the two cycle diagrams on the pressure volume matrix and on the temperature entropy matrix. Now, we have said that in the Brayton cycle or Joule's cycle, the fluid is gas. The fluid is gas. And so we have the process where we have the fluid which is compressed. It's moved to a heat exchanger. From the heat exchanger, of course, whatever the pressurized gases are, they move into the turbine, expand, do work. Do work, reciprocating work is a piston. Work is reciprocating. Remember, the piston rod is connected to the crankshaft, and so it will be a reciprocating work in that particular case. And then, of course, there's the rejection of heat in another heat exchanger. That one that I've described is referred to as a closed Brayton cycle. Let's draw a schematic for it. Closed Brayton cycle. I need the spaces, so what we need to do is we will dispose of one. Let me just put the temperature, entropy, profile side by side, so that as we discuss, you are able to follow our discussion. 4, so we have 1 to 2, 2 to 3, 3 to 4, 4 to 1. Yeah, that. So we can dispose of this. Let's draw the closed Brayton cycle, so that see what it is. Here we have the pressure. Now, the closed Brayton cycle is consisting of a compressor and a turbine. You have exchangers, heat exchanger. Heat is added in here. And here the heat is rejected. It's another exchanger, heat out. So this is a compressor. This is a turbine. Of course, the compressor. The fluid is compressed, moves into the heat exchanger. Of course, heat is supplied. Of course, the gas becomes completely pressurized, then to the turbine. The turbine does work. And of course, whatever is exhausted goes to the heat exchanger, where whatever heat is rejected is represented as Q out, and then back to the compressor. And there we are, that cycle. And the compressor and the turbine, of course, they're interfaced through a shaft. So the work outputted by the turbine will assist in compression of your fluid. Assist in compression of your fluid. This is a shaft. This is a closed Brayton cycle. This is a closed Brayton cycle. You have the compressor, the fluid compressed, the heat exchanger, heat supplied, because they become highly pressurized, released in the turbine, expands, doing work, the pressure volume work, which you have seen in the piston cylinder model, which is normally a reciprocating work, and then of course the exhaust gases, the heat is extracted, and again the cycle continues. That is a closed Brayton cycle. So if there's a closed Brayton cycle, so don't confuse with the normal terminology of closed systems in thermodynamics, where we talk of a closed system as not being in allowing transfer of matter between system and the surroundings. That's now an amorphous definition when you come to dealing with cycles. So you got to be careful about that, because remember we talked about system, that part of the universe you have a special interest can be closed, no transfer of matter between system and surroundings. It's open if there is transfer of matter between system and surroundings, and is of course isolated if it is closed and there's no thermal or mechanical contact with the surroundings. So these are important. You can look at our very early lectures where we were introducing the basic terms in thermodynamics, and I encourage you to do so. Now, then it means definitely there is an open Brayton cycle. Open Brayton cycle. It's an open Brayton cycle. It differs from the closed Brayton cycle. How does it differ? Now there's the element of a fuel being put into the system in the combustion chamber, then it's ignited, you get the products which are completely under high pressure. Of course, they go through the turbine, and now you're familiar with the processes which take place in the turbine. So we have, in that particular case, we still have the compressor, we still have the turbine, we now have our combustion chamber, and that, remember, is our compressor, is our turbine. Now, we have air from the atmosphere getting into the compressor. It is compressed. I also encourage you once again to look at our discussions on air compressors. It is compressed by the compressor, and then of course the fluid is delivered to the combustion chamber. But in this combustion chamber, there's also fuel delivered. So there's a mixture here. And just like we saw, when you're dealing with internal combustion, it is ignited. When it's ignited, of course, you produce the products of combustion, which are high temperature and pressure, and they move to the turbine. In the turbine, there's work. And of course, there are the exhaust gases. So this is an open Brayton cycle. That's a closed Brayton cycle. Now, in terms of the efficiencies, remember, when we're talking of efficiency, the compressor takes quite a bit. Remember, they are interfaced with a shaft. There is a shaft there. You have a shaft. So the work from the turbine is also used to drive the compression. Now, very important for us to know that. Now, what is the efficiency of this process? One of the things that you can tell straight away is that because the work of the turbine will be eaten up quite a large chunk of it by the negative work of the compressor. And what is efficiency is normally outputted work over input. Now, if you just deal with in terms of temperature and we look at the efficiency from the Carnot system, remember, let's just continue drawing our circles so that we have 2, 3, 4, 2, 3, 4. We know what the steps are. So in terms of efficiency, in terms of the lowest temperature, the 1 minus T1 over T3. 1 plus T1 over T3. Best illustrated in the entropy temperature diagram. 1, 3. That corresponds to that. So that really basically it is T3 minus T1 over T3. But if we compute the work done, compute in terms of work, assuming steady state processes, assuming steady state process, we remember from steady state process that dH plus dC squared over 2 plus d dz was Q plus or minus W. And so, because kinetic energy is not an issue there, we can ignore it, it's not significant. Potential energy, we can ignore it because there's no significant change in the position from a datum level or some reference position. So we can also assume that it's 0. So that dH is equals to Q plus or minus W. But remember that we are talking, when you're talking of the compression and expansion processes, they were adiabatic or isentropic, so that Q is 0. They are adiabatic stroke isentropic. And we have already explained several times based on Clausius inequality, the fact. Therefore, if we compute from the system, yes, compute from the system 1, 2, 3, 4, 1 to 2, 2 to 3, 3 to 4, 4 to 1. If we compute our work for the compression and for the expansion, then based on this expression here, we can see that for step 1 to 2, we have dH is H1 minus H2. And what is dH? What is dH? Remember, dH is Cp dt. So it is Cp into T1 minus T2 for the work which has been done for compression. And similarly for the turbine. For the turbine, dH, that is step 3 to 4, step 3 to 4 for the turbine, again we use the same expression, dH is H3 minus H4, and that is of course Cp T3 minus T4, that is W turbine. So that if we work with this quantity, and what is the work inputted? Remember, we have the heat exchanger and we input heat into that particular system. So therefore the efficiency is work, the turbine, plus that of the compressor divided by Q in. Q in. Now, let's put in the quantities. Remember, for the other steps, which we didn't go through, step 2 to 3, step 4 to 1, still have same process, H2 minus H3, H4 minus H1. And of course, in terms, capacity again will have Cp into T2 minus T3, Cp into T4 minus T1. But we are focusing on those components where we're doing work. So that later now, this is the efficiency. That particular case of the turbine, we have said, is Cp into T3 minus T4 plus the turbine T1 minus T2 divided by Qin, which is H2, which is Cp into T2 minus T3. So we are able to compute the efficiency of that particular system. We are able to compute the efficiency of this particular system. But now, in terms of pressure ratios, we can use the expression which we got when we solve for adiabatic reversible work. Look at, I encourage you to look at that particular lecture for adiabatic reversible work. For adiabatic reversible work, we saw that T2 over T1 was equals to V2 over V1 gamma minus 1. What was gamma? Gamma was the ratio of the heat capacity, isobaric over isochoric heat capacity. That's the ratio of the heat capacities. So, based on those particular quantity, we can push to get the efficiency in terms of the pressure ratio. Pressure ratio, remember from Boyle's law, pressure is inversely proportional to volume, as Boyle's law. Let's remember that. Then it means that we have T2 over T1 is equals to V2 over V1 gamma minus 1 in terms of pressures. That is the same as P1 over P2 gamma minus 1. Gamma minus 1. So that, what does that mean to us in terms of these particular quantities? If we remember, in our cycle there, pressure, volume, you must always have the cycle in your mind. 1, state point 2, state point 3, state point 4, 1 to 2 compression, 2, this isobaric, this is compression, this is expansion, 3 to 4, this is compression, and this isobaric is isobaric. What does that mean for pressure volume profile? That P, because this is constant, that's called P2, and this one P1. So it means that pressure at point 2 is equals to pressure at point 2, state point 2 is equals to pressure at state point 3. And that's from this diagram here. And pressure at state point 1 is equal to pressure at state point 4. So simple arithmetic, if we take this ratio, we have P2 over P1 is equals to P3 over P4. And that is the pressure ratio. So what does that mean? What does that mean to us? We need to work with this system there. So we are saying that in terms of pressure ratio, we can now write and say that actually the temperature T2 over T1, which is equals to P1 over P2 into gamma minus 1 can be written as, remember, the ratio of pressure is P2 over P1, so we can have that as 1 over Rp into gamma minus 1. And you can repeat that process where you are relating the temperature in the circle to the pressure. And of course, once you compute these values, for example, now we have here T2. This T2 here, for example, we have therefore T2, for example, T2 over T1 is 1 over the pressure ratio raised to gamma minus 1. So T2, for example, is T1 into 1 over Rp, 1 over Rp into gamma minus 1. This quantity for T2, you can plug it in the efficiency expression here. So you have to solve for T3, you have to solve for T4, T1, we have the values there, you can get that. You have already the expression involving T1 and T2. Now in the same way for T4, T3 and T4, just remember from our diagram again, we go back there. What did we say? We go back there so that you are not lost. 1, you have 1, state point 1, state point 2, state point 3, state point 4, 1 to 2 compression, 2 to 3 isobaric, expansion, isobaric, isobaric. Again, remember, pressure called P1, this is called P2. Again, we have here now P2. P2, we say that pressure P2 is equals to P3. And pressure P1 is equals to P4. And we can work with the ratio again, where we say, again, P2 over P1 is equals to P3 over P4. And still use the expression which we had said, which relates the temperature and the volume. The temperature and volume, remember, which we have said for adiabatic, reversible, temperature T1, T2 is V2, V1, gamma minus 1. And the same is true for the other temperatures, that is temperature T1, T2, T1, T2, you can do it for T3, T4, and you get in the values of those temperatures and plug them in. And of course, you get much more bulkier expression and you'll have this, but you are able to show how the temperature relates to the pressure in this particular cycle and how it is in terms of efficiency. So you find, for example, if you increase the compression ratio actually affects the performance. So you want a situation where you want to look at the compression ratio so that you have a case where you have an extended expansion. If you have an extended expansion process, you are going to have, let's just illustrate it a little bit more graphically. So if you have depending on the compression ratio, it has to do with the volumes of the cylinder and that of the combustion chamber. You want, if you prolong it, you do more work. You definitely do more work. And of course, you'll have increased the thermal efficiency. And even the ratios of the fuel and air which the system takes will be significantly reduced. And those are the things which one look at in terms of modifying so that a system becomes much more efficient and in terms of consumption of whatever energy system, whatever you're using as your fuel system. This case, for example, where you have air and fuel mixed in the combustion chamber and what. You just look at the ratio of the piston, the volumes, the cylinder volume, and that of the combustion chamber, and moderate them in terms of based on your calculations, and it will improve some of those performances in terms of efficiency. I think we'll stop at that particular point.